Right, there we go. We're recording. Yeah, kind of feeling slightly under the weather at the moment. Which is like, I don't know if that's kind of an international saying or not, but in England that means kind of you're feeling slightly ill. Um, and the reason for it is that at the moment it's crazy cold here. Normally in a normal year for us, it might be like the hottest it gets is like 30 degrees Celsius, um, which is probably like 80 degrees Fahrenheit, 85 degrees Fahrenheit. I don't know if you guys use Fahrenheit or not. Um, do you use Fahrenheit or degrees Celsius? Oh yeah. So yeah, for it's reached a low yesterday of -4 degrees Celsius, which I don't know if that's normal for you guys, but for us that's like unheard of. So everybody seems to be getting ill. Everybody's got a cough and sniffles and so on. So yeah, you'll excuse me if this ends up being a bit shorter or end up coughing up a lung halfway through. Um, right, I've got to get rid of this somehow. Um, slideshow and play from start. Wow, the coldest it's ever been. Yeah. Wow, that is 4 degrees Celsius in the winter is a record. Wow. Yeah. It's weird, like living somewhere like England where I guess it's quite famous for it, but also the temperature is just so mild. Like it normally, at least when I was younger, kind of 10 years ago, 15 years ago, the hottest it would ever get in summer is like 26, 30 degrees Celsius, and the coldest it would ever get is like maybe 0 degrees, maybe -2. Like if it snowed, it would be like, wow. It's probably only snowed 4 or 5 times in my lifetime here. Um, but like you do notice the kind of climate change. The British weather is very different than how it used to be. It's quite scary, actually. Do you, do you guys have anything like that? Is there any? That's crazy. Oh, 52 is madness. Wow. Okay. Yeah, you win on that front. 30 degrees isn't that hot when you put it like that. Um, yeah. Wow. Okay. I'll stop my waffling. I'll let you get into the physics here. So today, kind of thought it might be quite interesting to talk about dark matter and dark energy. We talked about stellar structures and stuff like that, kind of the cosmos and the universe. And so I thought it might be interesting to now touch upon what is the kind of cutting edge of astrophysics. I'm going to kind of caveat all of this, or not caveat. I'm going to preface all of this with there's going to be a lot of the truth is we don't know. So when you start trying to ask the hard questions, stop giving you answers. That's why. It's because we don't know. But anyways, let's get into it. So I guess the first question should be, why is there dark anything? You know, the concept of dark matter is that it's matter we can't see. Um, it's matter that doesn't interact with electromagnetic radiation. So, in that meaning, visible light. Oh, there we go. In that we mean visible light. We mean radio waves. We mean X-rays. We mean all of the stuff that classically we use for astronomy. Um, so all of our kind of current telescopes don't tell us anything about dark matter. Um, well, not directly anyway. So the reason we think dark matter exists, and to be honest with dark matter, we're fairly certain it exists. Dark energy is where we get a little bit more unsure. But with dark matter, the reason we think it exists is when you look at the spiral structure of this galaxy, these galaxies, and I've got a link here to show you what I mean. Sorry, 2 seconds. The link is loading up. Right, and now and share this screen. Here we go. So, oh no, where's it gone? Oh, it's so annoying. Hold on. This, right. So these spiral galaxies look a lot like this. And the reason it's blurred is that there's so much light coming off them that it's really hard to really hard to infer what light is coming from where, and it makes the image a bit distorted. But what you can see is a clear kind of anti-clockwise rotation of the galaxy. Now, from the light we can see, from the mass we can see, and you can kind of treat the two terms interchangeably here because the majority of the mass of this galaxy is going to be held within the stars within it, right? We're happy to say that stars are the most massive objects that we come kind of into contact with, the exception of kind of galaxies and black holes and supernova. But galaxies are formed of stars and supernova are just old stars. So it's purple in color. Anything in space having purple color has the hottest temperature, right? Yeah, precisely. So um, this really bright region here is the incredibly hot bit, and as you say, the more intensity here is the kind of hotter parts. But yes, like you can see you see here some orangey parts. Um, those are potentially supernova. They're so big at like this galaxy will be billions of stars. So the idea that you can see an individual bright spot, it has to be something incredibly intense and incredibly bright. Um, but within our galaxy, within our solar system, sorry, 99.97% of the mass of the solar system. So huge percent. You mean you'd kind of round that up to 100% at that point is kind of held within the sun. So to kind of when you view an image like this, to simplify it and say the stars are where all the mass is, isn't a really bad simplification. So if we look at all of the bright spots we can see, the stars in this image, we would expect a galaxy to rotate something like this, with the speed of rotation being proportionate to the distance from the center of the galaxy, and to be proportionate to the amount of mass held within that radius. One relatable question: do you know about Phoenix A, which is a black hole? I can't say I do know about Phoenix A. No. What did you have a kind of question or a fact? Must admit, I haven't studied Phoenix A, so I kind of couldn't speak towards it. Also, that's annoying, isn't it? Yeah, so what we'd expect from the matter we can see is that all galaxies with a kind of similar structure to this, which is kind of quite a pretty common structure, must rotate in such a fashion where the inner bits are rotating fast, and as you get further out, it starts to rotate slower. And you'd see this curve here, where this is velocity and this is position, I think, or radius, and it rapidly increases because in the center it's not actually going to be spinning that fast because it's not going to be moving that fast in a linear fashion because it's not got that far to move, so it can rotate very quickly without moving very far. And once you reach that kind of peak, probably about here, everything else is going to slow down in the manner in which it rotates, like this. A very reasonable assumption. But what we see in reality is that these spiral galaxies rotate far more like this, where it is spinning very quickly in the center, but actually the rest of it is kind of pretty much keeping up. And whilst it isn't keeping up, it is traveling, and this is the difference between linear velocity and rotational velocity. It is traveling quick enough to have the same linear velocity. So whilst it's getting left behind in terms of if you drew a line, at each point, you're going to be looking at a new part of the outer bit. It's traveling at the same linear velocity. Yeah, sorry, that is not very helpful for me, but yeah, I'm afraid I haven't heard of it. But it's traveling at the same linear velocity. And based on our understanding of gravity, our understanding of how these objects rotate, which we think we understand quite well, there must be a greater mass distribution towards the edges of these spiral galaxies than we can see with the visible eye. Because we can see all of the stars, we can see all of the hot gas. We know that it shouldn't be spinning this fast. And this understanding that there must be something causing it to rotate in such a uniform manner is what we call dark matter. It's just matter that we can't see, that we know must be there. It must be in these outer fringes. And it's inferred via gravity, by the observation of visible matter. So whilst we can't image it directly, we can see it. We can see its effects. And whilst this is a bit abstract, it's not actually an uncommon method of visualizing something. You know, if you look at a river, sometimes you can look at a river and it can look like it's flowing, but it can look very calm and stationary. But if you were to drop a stick, you were to jump into it, you'd realize that actually, like, beneath the surface, there's so much going on that we just can't see. And it's not until that you observe something that you can see something physical, like in this case matter, or in our case a stick, you can really see how the water is behaving. Well, that's exactly what happens here. And like I say, this is dependent on our understanding of gravity being correct, because we're basically saying that all of the other orbiting objects we've seen, kind of planets, moons, artificial satellites, all of that stuff, we think we understand gravity, and therefore we know that these shouldn't orbit the way they do. But it's like all of physics. Our understanding of this is dependent on our understanding of other things. However, our understanding of gravity is fairly sound. So, a further piece of evidence for dark matter is the cosmic microwave background. Now, I don't know if you've heard about. Oh, this image has come up rubbishly. I don't know if you've heard about the cosmic microwave background, but basically, all across the universe, no matter where it is, no matter how distant, this is the visible universe. This is the universe that we're able to observe using our telescopes and our microwave, our kind of microwave telescopes, radio wave telescopes. And to break this down, the cosmic microwave background, when we look at electromagnetic waves, you've got the kind of spectrum of different electromagnetic waves, and microwave is just a part of that spectrum. It's like saying the cosmic visible light background, or the cosmic radio wave background. Microwave background is just a part of the spectrum. So don't be kind of put off by this. And what this rubbish image here shows, let's see if I can find a better one. The reason I liked that one was because it had a temperature scale on it, but oh, come on. Right, so you can kind of see this as a bit clearer. You just get these random fluctuations with no real order or pattern to them. You know, you can say there's a cluster here, you say there's a cluster here, but there's still high intensity spots up here and there's dark spots everywhere. There is no real order to it. And the fact there is no real order to it is in fact the order of it. If that makes any sense. What I mean by that is it's fairly uniform. there's no trend or pattern. It's all hot at the top, and when you get to the bottom, it's dark. There's no significant patches, and what we can say to that is that the cosmic microwave background has some regularity to it. It's kind of uniform, um, and what this means is that if the cosmic microwave background is essentially the kind of floor plan of the universe, as the universe expands, so too will this ring of kind of cosmic microwave background. Um, then we can kind of say that it must have all expanded from some uniform point. Um, so what this means is, sorry, that's my housemate asking me to keep it down. It's a lot earlier than it is for you guys, but anyway, I'm afraid she's gonna have to deal with it. Yes, what we can infer is that there must be kind of dark matter that is stretching the universe from within. And again, this is something we're going to talk about in the next slide, but it must infer some kind of underlying structure to the universe, and that underlying structure is what we call dark matter. Um, this is quite scary. I didn't realize it was so recent. So in 1929, Edwin Hubble observed the universe was expanding, and Hubble Hubble is the guy that gives his name to the Hubble Space Telescope, the really famous one that's kind of been up in space for, I think it probably made this observation in 1998. I can't say that's for certain though. And the way Hubble observed the universe expanding is quite simple. He looked at a bunch of stars that kind of he knew were about the same. And the reason we can tell these stars are the same is we can look at their kind of composition of material. And when you look at these stars that you know should be about the same, we call them standard candles because you know their brightness and so on is the same. You could see that some of them were red shifted and some of them were blue shifted. Now, if you think back to our spectrum of light earlier, where you kind of had red light, orange, yellow, green, blue, if you take the middle part of that light and the light is traveling away from you, it's going to decrease the frequency of the light because the light is traveling away from you. And if it decreases the frequency of the light, it's going to blue shift everything in that spectrum. Does that make sense? So these standard candles will appear to be slightly more blue than they should do. And on the opposite side, if the star is traveling away from you, sorry, if the star is traveling towards you, then the light it's shining at you is going to be it's the same as the Doppler effect, but just with light. The light it's shining towards you is going to increase in frequency because it's kind of catching up to its own frequency. And so these standard candles traveling towards you are going to appear redshifted. Well, the interesting part, sorry, it's the other way. Oh, that's really bad of me. Blue shift is towards, red shift is away. Apologies. Um, the kind of interesting part here is that whilst there were a lot of red shifted objects, a lot of objects moving away from us, they're kind of, and that's what we'd expect with an expanding universe, which is what we kind of think we have at the moment using like the Big Bang theory. The rate at which the redshift is changing was increasing. Objects that were moving away from you began to move further away from you still, kind of at an increasing rate, which shouldn't make any sense because gravity should be pulling everything back together. If anything, gravity, a force that has kind of infinite range, as we've discussed before, gravity should be slowing down the acceleration of the universe. So this is our kind of really big issue. And this is where we have to try and use dark energy to explain it. Dark energy is being used to explain this expansion, and it's theorized to be pushing everything apart, accelerating the rate of this expansion. It's almost seen as like a negative pressure, a vacuum that is pulling everything out into space. Um, and it's very hard to make any tangible uh, measurements or anything like that of dark energy because we just don't know. Um, but um, we know that it must be a greater force than the force of gravity that's pulling us back together. I don't remember that you told us about it a while ago. Two pulsars, a combination make a black hole, right? Yeah, so pulsars are white dwarfs, kind of white dwarfs with unique properties. So two pulsars is enough mass if they begin to spin and collide together that can form a black hole, correct? Really, to form a black hole, you just need a spinning motion of any massive enough objects. So two white dwarf stars is kind of massive enough. And if you can think of anything more massive than those, in some off chance that a whole host of main sequence stars should collide together, potentially that can make a black hole. But you need lots of them. Anyway, yeah, you're right. That is what creates a black hole. Um, and this other interesting fact is that black holes today are 7 to 20 times larger than they were 9 billion years ago. What does this mean? Yes, they're growing, and that shouldn't be a surprise to us. We've seen them kind of suck in mass and grow. So 7 to 20 times larger maybe isn't that surprising. Um, but what is surprising is that when we look at these black holes that kind of we can see are growing, there's no visible matter near them. We can't see any reason that they should be getting any bigger, but they are. Um, and this goes back to dark matter, um, and their expansion can also be attributed in part to dark energy. Yes, exactly. Because a galaxy is a great example of something that's much more massive than a white dwarf star. Um, yeah, exactly. They can. I don't know the term either. They can essentially consume galaxies. A lot of galaxies have black holes at their center, which is what causes these kind of spiral galaxies. Um, yeah, and sorry, and this dark energy is deemed to be uniformly distributed. Um, we have no idea why or where it's come from. The going theory is that it's probably from the Big Bang, but we just don't know. And then finally, this is our inferred distribution of how much of the universe is made up of dark energy, how much is made of dark matter, and how much is made of actually visible matter, like stars and planets and gas clouds. Um, that's baffling. The idea that we can only see 5% of the universe. Oh, pardon me, sorry. Yes, you're totally right. It is called nucleosynthesis. Well done. Yeah. Yeah, it's kind of baffling. And these numbers are quite wishy-washy numbers. As wishy-washy as kind of large data sets and kind of complex mathematics can make them, but our understanding just isn't good enough to mean that these are really, really accurate. Um, but it is kind of baffling to think. Um, and that is kind of the end of this session. Apologies, it's a bit short. I'm feeling a bit rough, but if you have any questions, please feel free to fire away, and I can do my best to answer them. Yeah, go on. If you kind of refer, um, yeah, if you like to ask about some images, if you send them on the WhatsApp group chat, I can I can talk about them. Kind of I'm not allowed to message kind of pupils individually. But if you send messages on the WhatsApp group chat, can try and talk about them. Yeah, go on. And what's the kind of question? Yeah, yeah, that one. Or let me see if I can kind of just trying to show this so that other students can get a reference of what we're talking about. So that's what we're talking about. Your boss is playing. So why does this happen every time? Um, well, so that will happen because that kind of rubber, the black rubber bit inside, is going to be at a greater pressure than the air around it. And that's what makes the ball hard because that black inner piece is always looking to expand. Um, and the kind of lowest energy state it can get to is fully expanded. So when you weaken the exterior of the ball enough by kind of playing with it a lot and it gets kind of grazed and cut and whatever, eventually that inner piece is going to try and push through to try and get to a lower energy state because it's going to try and equalize the pressures from within it and the kind of outside world. And that's why it kind of bursts through. Then your second question was about according to the theory of downforce, when a Porsche 956 reaches its maximum speed of 321 kilometers an hour, it could theoretically drive on ceilings. Um, yeah, I guess so. I kind of don't know enough about this individual car, but what I can say is that it's yeah. With the second question, the concept behind it is just that as kind of assume that the car is some horizontal surface like that. As the car drives into the kind of static air at 321 miles an hour, it's the equivalent of static air blowing on the car at 321 miles an hour from a kind of air resistance perspective. And as it blows on the car, as it blows on some surface like that, the wind is going to be deflected up and kind of equal and opposite force is going to mean that the car experiences if this is experiencing some vertical force, if it's experienced some vertical force on the wind, then the car must experience the same downwards reaction force on the car. So that's why if the car was driving normally, it'd be pushed down. Now, if we flip the car the other way, so it's like that, wind is going. Oh, sorry, no, car's going to be like that. Oh, is it? No, the car is going to be like that. Uh, right, car's going to be like that. There we go. Eventually, you kind of got a really rough car with its kind of its bonnet and windscreen sloping towards the floor, which in this case is the ceiling. This is not a very clear explanation. But as the wind hits the car, it's now the wind is going to experience some downwards force here. The car is going to therefore experience some upwards force. And once the size of the upwards force becomes greater in magnitude than the force due to gravity, so kind of mass times gravitational constant, the car will stay where it is, or it will actually accelerate upwards. Um, and so it's just a matter of with the angle of the front of the car, the shape of the front of the car in kind of a real world case, and it's just what wind speed do you need in order for that speed to kind of cancel out the mass of the car. So why is it only this car able to do it? Well, it'd be a few factors. One, it will be to do with the shape of the car. How aerodynamic is it? How well does it kind of experience this downforce? This downforce. If you had a lorry, a big kind of truck with a flat front, when wind hits it front on, the wind isn't going to create any upwards or downwards force because it's just hitting a flat surface, right? So that's why this car, and it'll also be a component of 321 kilometers an hour is very quick. So a lot of cars can't reach that speed, and therefore they can't experience that same force. Does that make sense? Awesome. Any other questions, guys? No? Okay, in which case, I'll let you guys go. I'll let you go enjoy your Saturday afternoons. Um, in my opinion, is teleportation possible? Oh, I must admit, I don't know. I really couldn't say. If you leave it with me, I'll have a look at it. But I must say, it's just something I've never really studied or looked at before. I don't want to kind of I don't want to misinform you. I mean, if Einstein says it is, that's probably quite a good opinion to have, isn't it? I'd be I'd be brave to disagree with Einstein, but I tell you what, I'll I will go away and I'll have a little look at that, and I'll get back to you, and then we can maybe talk about this in the next lesson, or I'll send a message on the group chat and I'll tell you what I think. But I'm not sure. I'm not sure in a position to be disagreeing with Einstein. Oh, I see. I see. Well, then theoretically, it's possible. If that's the only requirement, you need to be able to travel at the speed of light. Theoretically, it's possible, but it's just in practice, can we do that? Probably unlikely. Right. Okay, guys. I will. Oh, go on. One last question. I hope I know it now. I must admit, I don't. Um, what is gravity if it's not a force? No, does he say that it's some inherent property? But that would just be mass. I don't know. Um, right, that's getting added to the list of stuff that we can discuss then. We can talk about gravity and we can talk about okay. Um, right, guys, have a lovely Saturday afternoon. I will send you the answers to these questions via WhatsApp, and I will put this recording up there as well. Okay, bye bye. Have a good afternoon.